Now let's turn our attention to a topic of determining whether a sequence converges to a real number or if it runs off to infinity. So if it converges to a real number, what that means is as you let the value of n increase without bound, so you let n increase to infinity, the value of the function, or the value of the sequence terms, that is approaching a specific number and not just also running off to infinity. So by definition, what we say here is if we have some sequence defined where n is greater than or equal to 1, if there happens to be a real number L such that the limit as x goes to infinity of f of x equals L, then the series converges and the limit as n goes to infinity of a sub n equals L. Okay, let's look at some examples to try and make sure we fully understand what that means, because the concept is fairly straightforward, I assure you. Determine whether or not the sequence converges. If it converges, find its limit. Okay, so in order to determine if the sequence converges, ultimately, we just want to test and see if there is a value to the limit as we let n go to infinity of the function which defines the sequence terms. Now, how might that work out? Well, let's take a look at this graphically to make sure we fully understand. Okay, so we have 5 minus 3 over n squared, and let's take a look at that sequence. All right, so you can see in light blue here, there are the sequence points. So it's just taken values along the x-axis here and plugged them in and determine what they are along the y. Let me change the zoom here a bit. What you can see is that there is a trend that these points are seeming to approach a specific value. And in fact, it does kind of look to me like that specific value happens to be right at 5, because you can see that, you know, these points are approaching 5, but they never seem to really go past 5. Okay? So ultimately what that means, that's what that means. And we say the value of the limit equals L. That's this y value right here that the points are approaching. And you don't need this app to particularly see this happening. You can use your calculator and just look at a graph, but this app might help you visualize a limit point, using this dashed line. Okay, so now that we know what we're looking for, we can see how the analytics work out. Now, since we're doing a limit as n goes to infinity, if L'Hopital's rule applies, you can absolutely use L'Hopital's rule to evaluate these things. You can also use rules involving rational functions and how they relate. So one known property about rational functions is that the limit as n goes to infinity of any value divided by n raised to some exponent p, where, say, p is greater than 1, all right, that's going to go to 0. So we can use that property, and especially right here, we can see this right here, this is just a fraction where the denominator is growing, the numerator staying constant. The value of that fraction is ultimately going to go to 0. So the value of this limit is going to be the constant value 5. So this sequence then converges, and in particular, it converges to 5. All right, determine whether or not the sequence converges. If it converges, find its limit. All right, so here we have 3n to the 4th minus 7n squared plus 5 over 6 minus 4n squared. So ultimately what we need to do is calculate this infinite limit, which is essentially finding the location of a horizontal asymptote of this rational function. And as I said, you're welcome to use rules of rationals, or you're welcome to use L'Hopital's if it applies. And be careful, because it's easy to want to jump in and use L'Hopital's every single time you run into a limit, but it only works for limits of the type 0 over 0 or infinity over infinity. So in this case it would apply, but you can also use rules of rational functions here. So the degrees are the same, which means the numerator and denominator would be going to infinity at approximately the same rate, and therefore there is a horizontal asymptote, or an infinite limit, however you want to look at it, at the ratio of the leading term coefficients, so negative 3/4. That type of logic, however, won't work on functions that are not necessarily rationals. So in those cases, we might have to rely upon something like L'Hopital's rule. Certainly, graphing can help. If we wanted to take a look at the graph and see if we get an idea whether or not this function converges, we can certainly do that. Okay, so in this example, we have 2 to the nth power divided by n squared. When I draw this one, you can see the dots here. They tend to trend downward, but then they start trending upward again. And they're increasing pretty rapidly here. If I change the zoom settings a little bit, the thing about this is they're growing extremely rapidly here. And if I pick any point to be like the maximum, like if I said that they're approaching this value right here, and that's about, what, 47 or so. Well, as I zoom out further, no, here's another point which is much larger, which looks like it's around about 84. So the thing is, they're not really tapering off. They have to kind of have this tapering off in order to have the horizontal asymptote, or the limit at infinity. So I would say this particular series is running off to infinity, which means it diverges. So let's see what happens when we work it through analytically. So here I would use L'Hopital's rule, because if I'm doing the limit as n goes to infinity of 2 to the n over n squared, certainly the numerator as n gets large is going to infinity, and the same is true for the denominator. So applying L'Hopital's rule, which if you'll recall, tells you to just take the derivative of the numerator and the derivative of the denominator. Not using the quotient rule here to get this derivative, just doing the numerator and denominator separately. So the derivative of an exponential is basically itself, but you have to multiply by the natural logarithm of the base. So if you have e to the n, that would have just been e to the n, because you multiply by the natural log of e, which is just 1. But any other base, you just multiply by the natural log of the base. The derivative of the denominator, since that's linear, will be 2n, and this essentially is still of the form infinity over infinity. So it's still an indeterminate, and we have to do another round of L'Hopital's. Even if we're pretty certain what's going to happen here, we have to keep doing rounds of L'Hopital's until we get, something that is not infinity over infinity. All right, so the derivative of the numerator, I have 2 to the n, whose derivative is 2 to the n times the natural log of 2. Since I already have a factor of natural log of 2, that's going to make that constant a square now. And then in the denominator, I'll just have the constant value 2. So now the numerator is going to infinity, the constant, or the denominator is staying constant, which means the value of this limit is going to go to infinity. And if the value of this limit is going to infinity, that tells me that the sequence diverges, just like we saw graphically. All right, one more example here. We have 1 plus 4 over n raised to the nth power. So let's take a look at this graphically and see what we can determine from the graph. All right, so that's 1 plus 4 over n raised to the nth power. Now, when I graph this, doesn't look like much, but my first point is way up here. Okay, so that just means I need to change my zoom. Let's bring everything down. And it looks like things are growing pretty rapidly here. All right. But let's continue bringing some things down, and it looks like it might be actually tapering off, even though it is growing pretty quickly through here. If we were to, take a guess that the limit is about right here, I could even zoom the other direction along the x. Well, that goes higher than that. So let's try again. It's hard to really say whether this is actually approaching a value or it's not. It could be approaching a value. We do see that tapering, but it does kind of look like every time I choose a value, it sort of goes over that limit, which makes me think that it could diverge. But we do see a taper, so we really need to let the analytics and the mathematics tell us what's going on here. So let's take a look at that. Now this example, even with L'Hopital's rule, is going to be pretty tricky. And the reason is we have this exponent of n, and then we also have this denominator of n. So if we were to try and differentiate using L'Hopital's rule, we'd need a numerator and a denominator, but we don't exactly have that. So we're going to need to be strategic in how we evaluate this. So we're going to say y is some function 1 plus 4 over n to the nth power. Okay, now to get rid of an exponent, one thing that always works, and one of the main reasons we love logarithms, is that if we took the logarithm of both sides of this equation, we could absolutely take that out of, or remove that exponent and make it a multiplier. Because that's just a property of logarithms, that you can take an exponent on the argument of your logarithm and make it a constant multiplier. Or not necessarily, I guess not a constant multiplier, but a multiplier nonetheless. So n times the natural log of 1 plus 4 over n. Now, we have complicated things a little bit by introducing a logarithm, but I think we can do a little bit more with this particular function than we could the original with that was 1 plus 4 over n to the n. And here's why. If I try to come up with the limit as n goes to infinity of just the right-hand side, which is n times the natural log of 1 plus 4 over n. Here's something that I can do. I can rewrite this as the limit as n goes to infinity of the natural log of 1 plus 4 over n divided by 1 over n. Now, the reason I would do that is because as n goes to infinity, 1 over 4n is going to go to 0, so this is going to approach the natural log of 1, which means the numerator is approaching 0. And the denominator, as n goes to infinity, is approaching 0. So this is effectively something of the form 0 over 0, which is a type that I can apply L'Hopital's rule to. And that's what I'm going to do next here. I'm going to say that this is equal to, for L'Hopital's, the limit as n goes to infinity. Now, the derivative of the numerator, whenever we differentiate a logarithm, we take the derivative of the argument, which I'll just do in a second, divided by the original argument itself. And then that's going to be over the derivative of the denominator. So 1 over n, we can change that into n to the negative 1, and then bring the negative down, subtract 1 from the exponent. What we're going to get is negative 1 over n squared. So I'm just going to speed that process up. Now, the derivative of 1 plus 4 over n is actually pretty similar to that. So what I'm going to do is rearrange some terms here. Just try and simplify as much as I can. Alright, so the derivative of 1 plus 4 over n, similar to what we did in the denominator, it's going to be negative 4 over n squared. Actually, let me write it like that, over, and then we have 1 plus 4 over n. Now I'm going to multiply that by the inverse of the denominator, so basically just negative n squared, but I'll just write it negative n squared over 1. Alright, because what that will do is negative 4 over n squared times n squared. The negatives are going to cancel, and so will the n squareds. So I now have the limit as n goes to infinity of 4 over 1 plus 4 over n, which means as n goes to infinity, 4 over n goes to 0, so just this part right here goes to 0. So this limit will evaluate to 4 over 1 plus 0, or just 4. Okay, so that's a result. It's not the final answer, but it's a result, and it's getting closer to what we want. Now, back here, we said the natural log of y was equal to this thing. And we did a limit as n went to infinity of this part. So the natural log of y then is going to equal that limit. So it's going to equal 4. Now if the natural log of y equals 4, we can take basically both sides of this equation and make it an exponential function with base e. E to the natural logarithm of y reduces to just y, and that's equal to e to the 4th power. So what that means is this sequence converges to e to the 4th power. So even though we weren't really seeing it graphically, because as we kept zooming out, it still looked like we had larger and larger values, but there was sort of this tapering, so it was kind of uncertain as to really what was happening. We got to around 50 or so, I think, but e to the 4th power, what is that? Well, let's pull up the calculator and see. All right, so e raised to the 4th power works out to about 55, effectively, a little bit less than 55. So we were getting pretty close. We got to around 50, like I said, so we were getting very close to the actual answer there. But that is how we would determine whether a sequence converges or not. Ultimately just find its infinite limit. And you can use any method at your disposal, including L'Hopital's rule, in order to determine that.